With our two unknowns here, so we're missing two equations if we want to use this eddy viscosity hypothesis. And here they now jump directly to the two equation model. And here set up as a sort of a generic transport equation. You can always create this equation yourself. You want to have a transport of money. Change or rate of money equals somebody has to produce money, and somebody is spreading money around, and someone is using money. Last one shouldn't be too hard to find. So yes, you can make a transport equation out of anything. No problem. Of course, you have to model these terms then, of course. So that is now the question, how should we model it? For this equation, I don't think he wrote out the exact equation. No. Yeah, some terms, but not all of them. So just to show you, I jump to the other notes that you have been given, this lecture notes in Turbulence. Here you have the transport equation for K. And I think it's written out explicitly here on page 19 somewhere. Where is it? 17, 18, 19. Here we have it. So here you have it exactly as it should be. Written a little bit complex. You have some small q, which then is q is the square root of k. Okay, but the same notation. The large u's, that's the mean velocities. Small ones, that is the fluctuating parts. Small s's here, they are sort of messy. They will now be du dx for the fluctuating parts, so the stress tensors for the fluctuating velocities, and then time average. So finding this term, that's going to be a real pain. And here you have a pressure term together with the k, not easy, and here fluctuating velocity times the fluctuating stress, and then time averaged, and then taking the derivative of it. So finding the solution here for the analytical equation, forget it, can't be done. How to achieve this equation? Well, you can sort of modify and play around with your first, or the original Navier-Stokes, where you just insert this mean and the fluctuating velocities before you take the time average. And then you take the Rahn's equation, where you have taken the time average, and then take the difference between those two. You will end up with an equation for actually the fluctuating velocity. And then you add a fluctuating velocity to the entire equation, and then some algebra, you can end up with an equation like this. So yes, it's possible to find exact transport equations for almost anything. So here for K, but it doesn't help us. Here to the left, this is okay. This is the total derivative of K. No problem there. Also, the first term here. Here you have the Reynolds stress multiplied with the mean velocity gradient. This term is possible to handle. The rest, forget it. So we have to use a model anyway. So I believe that is why most modelers, they don't even bother to write this up. So they jump directly to this generic form and then say, okay, these terms has to be modeled. You can't use the exact analytical expressions. There has been I can address that one later. Anyway, I just thought you might want to see it here for once. Back to the two equation models, and here we have one of them, transport equation for K. So we need a production term, a diffusion, and something to eat up the turbulent kinetic energy. So for the production term, as I said, here we can use the eddy viscosity hypothesis once more to substitute for this Reynolds stress, and then we have an expression for the production term which is then quite correct. Of course, it involves still this unknown eddy viscosity, but the rest, that is just mean velocities which are unknown already, so he doesn't introduce anything that we have to model anything more than this. So the production term, he will be quite okay. For the diffusion term, that's a little bit more tricky. That one has to be modeled. And then what we are missing here is the dissipation. Diffusion term, okay, we have fairly decent models how he will look like. For the dissipation, well, in the two equation models, you don't try to model him directly. You create or find him from a transport equation of his own. So then you need a transport equation for epsilon. That is also possible to find. I think also he was here somewhere. Let's see, diffusion terms. Yeah, here we have typical models for how such a diffusion term can look like, involving again the eddy viscosity, and here a constant sigma k. Let's see how the transport equation for should be here somewhere. Oh, he hasn't taken them there. I can show it to you. It will look something like this. The rate of change of epsilon equals, and then you have, to say the least, a pretty nasty equation system, where you have no way to find good expressions for all these different terms analytically. Forget it. Very tricky indeed. So you throw all this away, and then you just use a simple model, production and diffusion and also dissipation. That's something that always puzzled me. Let's see if we have it here somewhere. No, we don't have it. Okay, but anyway, a transport equation for him alone, for epsilon, you will have the exact same form. It will just read total derivative of epsilon equals production term of epsilon, and then you have a diffusion term of epsilon, and also there you will have a dissipation of epsilon. What's that physically? I mean, you can understand something that produces it, something that spreads it around, moves it around, but then something that destroys the destruction mechanism. Now we're talking philosophy. The dissipation of the dissipation. I'm not sure how you can interpret that. But it must be part of the equation, the transport equation. And of course, it must be modeled. So you have in the two equation models here typical model for K and models for epsilon. And these models will involve not that many parameters, but a couple of constants you can play around with, fine-tune your model. To close the equation system, they use this Kolmogorov. It's just a dimensional analysis actually, finding that we can express the eddy viscosity as a velocity scale, turbulent velocity scale, that's the square root of k, multiplied with a length scale. This epsilon can be sort of estimated as k to the power of 3/2 divided by, again, a length scale. And with a little algebra then, you find the eddy viscosity as k square over epsilon with one single constant. So that is the closure that we need to have enough equations for our unknown. K and epsilon is found by their own separate transport equations. Then we can find the eddy viscosity, which we then can put directly into the Navier-Stokes. Finish. Then we have a K epsilon solution to the problem. This doesn't look too smart, actually. You divide by epsilon. Very bad idea, isn't it? Imagine you have a region in your domain. Turbulent flow, and then over here, the velocity goes down, the flow becomes laminar. Laminar flow, epsilon is 0. How do you handle that one? Very bad idea. So this model, he hates it whenever anything goes laminar. He can't really handle it. It's definitely a high Reynolds number model. Nevertheless, if you have a look into the source codes, you will always find they divide by epsilon plus a small little number. They don't mention it anywhere, but they have to do it, or else this will explode immediately. So they always cheat. And I think you have also somewhere here, you divide by k in this model. Again, terrible idea. We know k, turbulent kinetic energy, is 0, very close to the wall. Everything is going to explode here. So no laminar solutions mixed with the turbulent solution, the standard k epsilon will fail. He can't handle it. But of course you can cheat a little bit. Now jumping to the full Reynolds stress models. A full Reynolds stress model, I want a transport equation for all the different Reynolds stresses, all 6 of them. And the transport equation look in this quasi-symbolic form, it looks like this. Rate of change equals production, you have diffusion, and you have dissipation, plus a new term. This is called pressure strain, but also redistribution. I like the name redistribution, because actually that's what he does. He takes energy from one of these components and give it to some of the others. So if you added all 6 of these, you will get 0. So he doesn't produce any energy, he doesn't move it around, but he takes it from one of these components and can give it to some of the others. So a redistribution of energy, that's a very good way to look at this additional term that we have gotten. Again, just for fun, I have the exact equation here somewhere. So here, the rate of change of a Reynolds stress equals, and then the exact analytical expressions, how they actually look. And again, the production term, he is actually not a problem at all. You see, he will involve the unknown functions that are already unknown, multiplied with the gradient of the mean velocity profile. So here, this one we can handle directly, precise, correct. The rest of these terms, model it. You can't handle it. Here, pressure fluctuations multiplied with the gradient of velocity fluctuations, forget it. You have no idea how this term looks like. And here you see this phi ij. So this will be this pressure strain term, or redistribution as I like to call it. Diffusion terms have a derivative in front, as it should have. It's always on a conservative form, because a redistribution, a diffusion term, you can always use the divergence theorem here to write it as a surface integral, so the derivative has to be in front of it. But he involves things like triple correlations. How does this term behave? Nobody has any idea. They tried actually some years ago, many years ago actually, when they first had this equation. Then they did the same, but now looked at a transport equation for a triple correlation. Then we need a lot of pages to describe that one correctly. And of course, a transport equation for 3 will then involve on the other side 4. Then you need a new transport equation for the 4th order, and so on. Of course, more and more messy, more and more complex. Then the philosophy went as follows. We have to model such transport equations for these very complex products here that we can handle. But okay, if we do bad modeling there, the effect won't be so hard when we use them in this model. They're going to do a lot of wrong here anyway, so it should make a decent result anyway. That was the philosophy, and then it's fairly correct, but the model was way too expensive and not in practical use either way. So you can have a look at it and then forget it, except the production term. That one is exact. That's precise. The rest we have to model. We can't handle this one. And also, if you took this sheet and went into the lab and asked the guys, can you please measure these so I can have an idea how they look, you will be thrown out of the lab. Measure pressure fluctuations multiplied with gradients of velocity fluctuations in the same point. How the heck do you do that? When you measure pressure, you have to enter the flow with a sound or something. Then you disturb the flow. You can't measure pressure and velocity in the same point. So no, they don't like it. It's very complex to measure this one precisely. So we can see the equations, yes, but we can't do anything about them. So okay, first term production, that's okay. We can have that one exactly. This pressure strain term, redistribution, has to be modeled. Diffusion term has to be modeled. And then we have the dissipation. Actually, each of these 6 different functions have their own private dissipation function. But that's sort of overkill here. So we make it easy. They all get the same epsilon, and then we use the same transport equation for epsilon as we did with the k epsilon model. So here, this will now represent 7 traditional 7 transport equations. 6, one for each of these Reynolds stresses, 1 for the dissipation. So here you have the precise production term, And as I said, he doesn't involve any new unknowns, so this one is perfect. But the rest we have to model. Now, as a very cheap alternative, instead of using a full RSM, you use algebraic stress models. I know some of these commercial codes, they had a list with different turbulence models, and among them were listed radon stress model, RSM. In fact, it was an ASM, so they cheated. That's commercial for you. So they used an ASM. Okay, this one is, of course, a Reynolds stress model, but it's just an algebraic one. A full Reynolds stress model, that's pretty advanced. I don't think you find it in Fluent, CFX, Star CCM, or any of those on a full Reynolds stress model. ASM you can find. And that's a very cheap expansion in your case. You start with K epsilon, get a solution, and when you have the solution, you switch on the ASM. The ASM can be something like this. It's just an algebraic equation system where you put in epsilon and K to find the 6 different functions, the 6 different Reynolds stresses. And now why should you do this? Why is this so much better? Why can he cover more physics than the standard K epsilon model? Well, the problem for K epsilon is that he is blind for directions. Remember, you have the turbulent kinetic energy, K. That's velocity squared. So you can say that a motion, he has a high kinetic energy, but you can't tell which way he's moving. So it's not a vector equation at all. While here you have components in the different directions. So the K epsilon, you might say, is based on the fact that the turbulence should be homogeneous, should be isotropic. You have the same turbulent intensities either way you are looking, which in many flows is a big lie. While this one, he can have different components depending on the different directions. So the ASM, he has a sense of direction, K epsilon has not. That's an important jump up into more complex flows. And it's very cheap, just a set of algebraic equations. So if you first have a K epsilon solution, if you have a possibility, then switch on the ASM and just see, do my solution change much? If it doesn't, okay, then the K epsilon was good enough describing the physics you are interested in. If you have changes, then you can say the K epsilon is bad for my problem. I obviously have maybe several regions where the turbulence is going to change with direction. It's definitely inhomogeneous. It's not isotropic at all. So this algebraic stress model may capture it cheap. And then, of course, it's a question if you actually should jump to even the next stage, finding a full Reynolds stress model, which can be hard to find, I think. Yeah. Okay, that was sort of the background theory for the ASM, RSM. Any questions? That's okay. So in this paper, they now focus a little bit in hydraulic machinery and in pumps, turbines. You have a lot of curved surfaces and you have a lot of rotating channels, typically in combination. So there you have some classical examples where we know K epsilon is going to fail and also K omega will have problems in these geometries. So you should use the proper turbulence models. I think you find a list here, if I recall correctly. Let's see. Okay, epsilon models, advantages, disadvantages should be all in the end here somewhere. Yeah, advantages, disadvantages for the two equation family, K omega, K, KL, K epsilon should also be listed here somewhere. So where they are good and where they are bad. K epsilon is currently the most popular two equation model, and here for two reasons. This epsilon equation can be found from the Navier-Stokes, but so can all of the rest, so that's really not an argument. The reasonable value here for experimental data, I would say the basic or main reason why most people choose K epsilon is that you find a lot of documentation of it. So I think that's the main reason. And these models, K epsilon, K omega, they give decent results. Two-dimensional boundary layers, jet along walls, 2D jets, wakes, mixing layers, plumes, tubes, channels, diffusers, anally, and also several three-dimensional flows, as long as you don't have too strong swirl, too sort of big vortices inside, not too high density variations, no chemical reactions, that's a topic of its own. And buoyancy-driven flows, low Reynolds number effects. As soon as you talk low Reynolds numbers, remember these two equation models, they don't like it. They are designed for high Reynolds number. So if you have a Reynolds number that is low, still turbulent of course, but low, you should seek out special low Reynolds number models, definitely. So you can expand them a little bit to handle a little bit more physics. There's boundary layers on a convex concave walls. We'll have a look at the problems there. And if you have a strong swirl, strong recirculation zones, you have to do something in addition. You have to use a special version of these models, or else they will fail. Three-dimensional jets, gravity stratified flows, talking weather forecast, and of course chemical reactions, two-phase flow, tricky. Yeah. Two effects it has been focusing here on this in this article. First one, we have a quite weak curvature in the flow. So say you have a channel and then it curves slightly downwards. Not much, doesn't have to be a sharp bend, but just a slight curve. The other effect we are going to look into is rotating flow. So let's try with the curved one first. A curved channel. So you have a channel with a slight curvature, and then you send in your flow here, and then it's a question, what turbulence mode should you use? Your Reynolds number, you're based on say average velocity, and the channel width is big enough, 3000, 4000, okay, it's turbulent flow, so we need a turbulence model. Which one should we use? Well, what's going to happen when the flow makes the turn? How can he make the turn? Well, it's only one way. Somebody has to push him in this direction. So the flow have to set up a pressure gradient in this direction. Absolutely. So here you will have a change of pressure in the radial direction, then to balance the centripetal acceleration here. If you are going to make a turn, you have a centripetal acceleration, which now will go something like this. So that's sort of the average pressure field, just to make the turn. So this means high pressure on the top wall here, low pressure on the innermost wall. The velocity profile can look something like this, for instance, at least in the straight channel before we start making the turn. Now what's going to happen due to this sort of outer pressure driving force in our system? Of course, we need another pressure gradient here in the streamwise direction to push the flow through. That's a different story. Now I'm just interested in forces perpendicular to the flow direction. So now imagine you are sitting here. You are a fluid particle and you are operating in this direction with a given velocity, sort of in the average velocity there, going side by side with your neighbors, no problem there. Now all of a sudden someone kick you upstairs. I mean, we are in a turbulent flow, so you can be moved a little bit in any direction. So say somebody kicks you upstairs. Now what's going to happen? Up here you will be fast, because the other one that is living in this position here, they have an average velocity which is lower than yours. I mean, you came from a region with higher velocity, so you will be fast when you are up here. Okay, you will be fast. You will have a much higher, say, acceleration than the pressure, than your surrounding pressure gradient, which then is created to balance your curvature. So if you are pushed outside, you are too fast, this pressure gradient is too weak, so you will just continue to move in this direction. If somebody kicks you downstairs a little bit, then what happens? Well, then you will be in an environment where the other fluid particles will be faster than you. You are too slow. So this force here, the not centrifugal, the needed centripetal acceleration that you should have is now too small. So the surrounding pressure gradient is stronger, and then he's going to push you even further in the same direction. So either way, if you are pushed a little bit away from your peaceful environment where you have everything in balance, you will be pushed even further away. So with that, we conclude this is an unstable side. Now do the same argument down here. So somebody is kicking you, say, up. You have one velocity where you have balance between those two effects, the local pressure gradient and the centripetal acceleration. You are kicked upstairs. You will be slow. The guys moving here, they will be faster than you. So this one is now going to be too small compared to the local pressure gradient, so you will be moved back again. Or if somebody kicks you downstairs, then you will be fast. This one will be bigger than the gradient, you will be thrown out again, centrifugal force, and you will be pushed back. Aha, stable side. So you can use this simple image to sort of decide or define and see that one will be unstable, the other one will be stable. Here you will enhance the turbulence, down here you will suppress the turbulence. And if this curvature is maybe not so weak, can be stronger, or if this channel is fairly long, then actually you risk the flow becomes laminar on this side.
Excuse me?
Yep.
Where's the limit between stable and unstable gradients there?
Where you have the derivative equal to 0.
Yeah, okay, so it's the peak of the,
Yeah.
So it's always the center point.
No, because now try to draw the velocity profile.
Because in the beginning it's...
A turbulent velocity profile from wall to wall when we don't have any curvature. He will look something like this on average. It's fairly flat. That's a turbulent velocity profile. If you now increase the Reynolds number, this shoulder will be closer and closer to the wall. And if it's laminar, well then he will go something like this. So what will happen? How will the velocity profile look like? Here. On the stable side, the flow will tend towards laminar flow. He will be faster. Laminar flow, much cheaper to push things through a pipe. So he will look something like this. He will start then on this laminar parabola. On the other side, it will be more and more turbulent. This shoulder is going to get sharper and sharper. So he will be something like this. But then they have to match together, so you will have a very strange velocity profile. So there, it's not in the center, it will be here where you switch stable, unstable. So here, tending towards laminar flow, here more and more turbulent. You enhance the turbulence. Try to do this with K epsilon. He has no idea what's going on. He doesn't see the difference between those two sides at all. So K epsilon here, no. Since he will be based on the fact that the turbulence should be homogeneous, should be independent of directions. And in this problem, absolutely not.
The gradients of like the average velocity goes into the K epsilon mode, right?
Yes, that's true.
So then connect them so I know where it is.
You mean here?
K epsilon can see this profile, right?
No, I don't think you will see the effect of this curvature at all. If you send in a laminar flow, of course you will destroy this parabola. It won't look something like this, but it will be a little bit distorted just due to the curvature itself. That can influence the turbulence a little bit, yes. But you won't get this unstable, stable picture at all. He can't handle it. But for this problem, very cheap, switch on the ASM. There you have it. He can handle this, no problem at all. But K epsilon, K omega, no. They will have real trouble with this weakly curved channel flow. And it can be shown, this curvature doesn't have to be strong. It can be very, very weak indeed. So if you say want to simulate the flow around an airfoil here, then K epsilon might not be a good idea. You have exactly this smooth curved surfaces. He can't handle it. K omega here would be better, but also he has trouble detecting the correct behavior here. Here actually I would suggest the one equation model is spiral mass is designed for wing. He gives decent results. If you find that he's not good enough, okay, then you have to jump all the way over the two equation models, and then you should use an ASM or a full RSM model if you want to get this one precise. Very expensive then. Yep.
Why would you choose a full RSM over an ASM then?
It's more advanced, definitely. Remember, you use the K epsilon as input, and then you adjust the solution with just a set of algebraic equations. And with a full RSM, okay, then you can actually have the more correct image that you produce a lot of turbulence here on the unstable side, but it is actually transported to somewhere else. And maybe during that transport process, being transferred into some of these other Reynolds stresses. The ASM can't handle such complex physics.
Would ASM be then the same as RSM, but you just remove the redistribution term?
No, because the ASM is not pure transport equations, just algebraic equations. So he can handle changes on the spot, yes. But he can't move things around. So, of course, much better than K epsilon alone, yes. But not as good as a full RSM. But a full RSM, that's rather tough. 20 to 25 parameters you have to find suitable coefficient set for. You have to search and then on the web to find a decent set of numbers. But not easy.
The stability of an ASM model, is it more generally like K epsilon, or is it closer to RSM?
No, it's not so fun to work with. You can easily explode in your face. As goes with all of these models. So also K epsilon is not necessarily so stable. So for such models you can try simulate first with a viscosity 10,000 times too big. Then you have a solution. And then you set in the correct viscosity, and then you can switch on a simple model. If you have a simple model available, like a zero equation model, Trantel's mixing layer or something, and then get a solution, and then sort of more and more advanced models to keep it stable. That will be one way to help softening down your problem. So if you are going to use, say, a full RSM, yes, then you might start with K epsilon, switch on an ASM, finding all the Reynolds stresses from the ASM, and then finally switch on a full Reynolds stress model. That could be a very good idea, actually. Other questions? We take a break.